In this lesson, we will learn how to solve inequalities. You can solve inequalities in the same way that you solve equations, with just one exception. If you multiply or divide both expressions by a negative number, you must flip the inequality sign. Otherwise, we're going to use the exact same steps that we use in solving a linear equation for solving inequalities. You just have to watch out for when you multiply or divide by a negative number, you flip the sign. Let's take a look at some examples to see how this works. So what we will be doing here is solving an inequality and graphing the solution set. The first inequality that we will solve is a plus 5 is greater than 8. To solve this inequality, we will use the same steps that we use to solve a linear equation. We'll go through all of the steps. Step 1, simplify both expressions. I can't do that. They're both already simplified. Step 2, get your variable in one expression. My variable is a, and it's already in one expression. Step 3 is to get your variable alone. And the first thing you do is move all terms without the variable to the other expression by adding the opposite. We have terms, things being added, and we have an a being added to a 5. So those are my terms. This term has my variable and this term does not. So I'll move the term without my variable to the other expression by adding the opposite. I'll add the opposite of 5 to both expressions. This will leave me with, in the left-hand expression, just a. I bring down my inequality sign. This says is greater than. Now, I know that I don't flip the sign because the only time that I will ever flip the sign is if I multiply or divide both expressions by a negative number. And I didn't multiply or divide. I added, so I'm not going to flip the sign. In the right-hand expression, I have 8 plus negative 5, and 8 plus negative 5 is 3. I've got my variable alone, so I now know that a, whatever it is, must be greater than 3. Now, I should not put this in set brackets because 3 is not a part of my solution set. A could not equal 3. A has to be greater than 3. So to visually see the solution set, I'm going to graph it. This says that a is greater than 3. So I can graph this on a number line. So I'll set up a number line here. And I know that a must be greater than 3. That means that a cannot equal 3. So a could equal 4, a could equal 5 or 6 or any number greater than 3. But it could also equal numbers like 3.5 or 3 1/4 or 3 1/10. A could equal a lot of different things. So to show what a can equal, we're going to put an open dot on 3. The open dot means that we cannot include 3 as part of our solution set. A cannot equal 3. But when we shade to the right, we're showing that a can equal anything that's greater than 3, but it cannot equal 3. And we put an arrow at the end here to show that it can be any number greater than 3, extending all the way through infinity. When we put an open dot on 3 and shade to the right, that includes all the numbers like 4 and 5 and 6 and the obvious ones. And it also includes 3.5 and all the numbers that are just barely bigger than 3, including 3 1/10 or 3 1/100th or 3 1,000th. All kinds of very, very small numbers that are just barely bigger than 3. We can check this by plugging in any one of the numbers that are in this solution set. So this inequality, the original inequality, is a plus 5 equals 8. So we can check this by plugging in a value from our solution set to make sure that it makes this inequality true. So you can pick any value you'd like to. I'm going to go ahead and pick 4. And if I simplify the left-hand expression here, I should get a true inequality. And this will say 4 plus 5, which is 9. It'll say 9 is greater than 8, and this is true. So this is evidence that my inequality was solved correctly. Now, you could check as many numbers as you'd like to because there's an infinite number of numbers in the solution set. So you can check this by making sure that the numbers in the solution set do make your inequality true. Let's take a look at another example. Negative 3 times a minus 9 is greater than 6. Again, we will use the steps that we normally use in solving an equation, except we have to remember that if we ever multiply or divide both expressions by a negative number, we must flip the inequality sign. So we look to simplify both expressions, and here we can simplify by changing subtraction to addition by adding the opposite. So we should do that first. This now reads negative 3a plus negative 9 is greater than 6. Next, we make sure our variable is in one expression, and it already is. So now we get our variable alone by moving all terms without our variable to the other expression by adding the opposite. This means that we will add positive 9 to both expressions. This leaves us in the left-hand expression with negative 3a. In the right-hand expression, we'll have 6 plus 9, which is 15. Now, since we did not multiply or divide by a negative number, we will not flip the sign. It will stay just the way it is. It will remain negative 3a is greater than 15. Next, we need to multiply both expressions by the reciprocal of the coefficient. The coefficient here is negative 3, and the reciprocal of negative 3 is 1 over negative 3. So we multiply both expressions here by 1 over negative 3. Now, I am multiplying both expressions by a negative number because 1 over negative 3 is negative. So, I now need to flip the sign. I'm going to do that right now so that I don't forget. The greater than sign becomes a less than sign. And then I simplify each expression after doing this multiplication here. We'll be left with a in the left-hand expression. And in the right-hand expression, we can write everything as a fraction by putting it over 1. I have a positive number times a negative number, which will give me a negative answer. And I can cancel. 3 goes into itself once, and into 15 5 times. This is 5 times 1, which is 5, all over 1 times 1, which is 1, but I never need to write a 1 in the denominator. So I've solved the inequality. Remember that whenever you solve an equation or an inequality, what you're doing is you're looking for the solution set, the set of values that you can substitute in for the variable that make the equation or inequality true. So now that we've solved this inequality, we've got our variable alone. This tells us that any number that satisfies this will satisfy the original inequality. Any number that is less than negative 5, when we substitute it in for a, will make that inequality true. Since there are so many numbers in this set, we generally like to graph the solution set so we can see what's going on here. So I'll make my number line. And since negative 5 will not make the inequality true, because it has to be less than negative 5, I start by putting an open dot on negative 5. This shows that we cannot include negative 5. But we can include any number less than negative 5. Since it's a less than, we should say shade to the left to show that any number less than, or to the left, of negative 5 will make the original statement true. So put an arrow on the end to show that this goes on forever through negative infinity, and that is how we would solve that inequality. Let's take a look now at a third example. This says 2a plus 4 is greater than or equal to negative 12. We'll follow the steps. I can't simplify either expression. My variable's already in one expression, so I'll move all terms without the variable to the other expression by adding the opposite. So I'll add negative 4 to both expressions. This will leave me with 2a in the left-hand expression. Since I didn't multiply or divide by a negative, I bring this inequality sign straight down. And negative 12 plus negative 4 is negative 16. Last thing I need to do is multiply both expressions by the reciprocal of the coefficient, and the coefficient is 2. So I'll multiply by the reciprocal of 2 in both expressions, which is 1/2. Now, I did multiply both expressions by a number. Look very carefully at the rule, though. You have to multiply both expressions by a negative number before you need to flip the inequality sign. We multiplied both expressions by 1/2, and 1/2 is not negative. Therefore, we will not flip this sign. The sign is going to stay just the way that it is, greater than or equal to. Now, some students seem to get confused when you have a negative number involved. It's not whether a negative number is involved in the multiplication. The question is, did you multiply both expressions by a negative number? And the number you multiplied by here is 1/2. That's positive. So this will leave us with a in the left-hand expression. And in the right-hand expression, it's going to be a negative times a positive, which is going to be negative. And cancel, 2 goes into itself once, and into 16, 8 times. So this will be 8 times 1, which is 8, over 1 times 1, which is 1. I don't need a 1 in the denominator. I find that a is greater than or equal to -8. This time, since it can be greater than or equal to -8, -8 is a solution. So I'll start by putting a closed dot on -8 to show that -8 will make the inequality true. And then I shade to the right, since I'm interested in the numbers that are greater than or equal to -8. So remember, the steps in solving an inequality are the same as those for solving an equation. Just remember, if you multiply or divide both expressions by a negative number, you must flip the sign.